Mm, myself means that I can substitute person and the department of electrical and electronics engineering at International Institute of Technology. Today we have learned about the subject on control systems engineering and not preferred IT, which is the subject for fourth semester, second year, electronics and robotics engineering for 2021 graduation. Today we have discussed on the topic frequency response analysis and our subject control systems engineering. This topic is an important frequency domain network physical analyze the stability and performance of control systems. Control. In this presentation, we will discuss frequency response and its characteristics, Nyquist plot and Nyquist stability criterion, border plot and border stability criterion. Frequency response strategies. The main methods of frequency response analysis are to understand the steady-state response of a system for sinusoidal inputs, to study frequency domain specifications, to learn how to construct border plots, and to analyze system stability using frequency domain techniques. Introduction. Frequency response analysis. Frequency response describes how a system behaves when a sinusoidal input is applied and the system reaches steady state. We vary the input frequency and observe how the output amplitude and phase change. Benefits of frequency response method. Some important benefits are no need to develop a complete mathematical model, direct use of experimental data, easy to perform with signal generators, helps identify complex system behavior, useful even for some nonlinear systems. Frequency response introduction into systems. For a linear time invariant system, input and output are later by the transfer function T of S. In frequency response analysis, we apply a sinusoidal input and observe the steady state output. So we given the sinusoidal input in the system, we get the output also sinusoidal. So how to find this transfer function? Laplace output variable, Laplace input. Generally, in frequency domain analysis, Laplace of sinusoidal output divided by Laplace of sinusoidal input. So like a subject is stable NJ system with a sinusoidal input of amplitude R and frequency W time W. So the input is R of t is equal to R sin omega t. We know that omega is angular frequency. Then a steady state output will also be sinusoidal. So C of t is equal to C sin of omega t plus phi. Here C is output amplitude, phi is phase shift. So the frequency remains the same, but amplitude and phase also change. Frequency domain representations. So by substituting S equal to j omega, the transfer function becomes T of j omega. This is called a frequency response function. It is a complex function and can be expressed in magnetic form, phase form, real and imaginary axis. So in magnitude and phase, for a complex number, magnitude is equal to root of real square plus imaginary square. For phase equal to tan inverse of imaginary divided by real. And for complex number means a plus jb format. In a plus jb format, we have to find magnitude root of a square plus b square. For complex number a plus jb format, we have to determine the phase angle is equal to tan inverse of imaginary divided by real. These are called gain characteristics and the phase characteristics. So here in this sample, we determine the isolation response for a system displayed with a differential equation. So we have seen one related problem. So here for a system described as a differential equation, b square yx divided by dt square plus 2 dx divided by dt is equal to y of t. Here we have to determine the steady state response x of t for a pure sine wave in t. So y of t is equal to 3 sine of 0.5 t. So here first we have to find the transfer function of the system. So here we know that we have to take Laplace on both sides in this differential equation. We have to find the transfer function. We know that the transfer function is equal to Laplace output divided by Laplace input. So we have determined the transfer function. Then step 2, substitute s equal to j omega in this transfer function. Then we have to calculate magnitude plot and phase plot for given frequency. So for magnitude plot, we have to find corner frequency. So the corner frequency we have to find from this transfer function. So corner frequency means in complex form we have a plus jb format is equal to real constant divided by imaginary constant. So in transfer function, how many terms in the uh, complex form, we have to determine the corner frequency. For example, three complex form in this transfer function means we have to find three corner frequencies: omega c1, omega c2, omega c3. Then we have to plot one table. We have to draw one table. In this table, terms, corner frequencies, slope, and changing slope. So terms means from transfer function we have to three terms means we have to write in three terms. Then corner frequency, we know that corner frequency, so corner frequency values. Then slope. For slope means j omega in numerator and denominator. Numerator means plus 20, denominator means minus 20. J omega square in numerator means plus 40, j omega square denominator means minus 40. So how to write it. Then change in slope column. In first point we have don't change in slope. So from second column we have to add these two values. We have to find the change in slope. Likewise, this till the table completion, then we have to choose the low frequency and corner frequency, high frequency. For we don't have analyzed these two values for this Bode plot.